So in this project, we'll build a classifier to predict the stroke cases using like GBM and XGBoost. So we can implement its features engineering, class balancing, and hyperparameters tuning to improve its performance. So for the part one question, to improve the performance of my classifier, I focus on feature engineering, handling the class imbalance, and hyperparameter tuning, and I applied one-hot encoding for categorical variables such as gender, um, work type, residence type, and the smoking status were converted into the numerical format using one-hot encoding, and bind numerical features such as age, BMI, and glucose level, and use SMOT to balance the data sets and ensuring the model learned from the both majority and minority classes effectively. So for model optimization, I use LightGBM as the primary model, which is well suited for the tabular data with categorical features and fine-tuned hyperparameters with grid search CV, adjusting the values like num leaves and learning rates and estimators to maximize the F1 scores. And additionally, I standardized the numerical features and to improve the model's learning process and ensure the better generalization and performance. So by implementing this improvement, I was able to boost the classifier predictive power while reducing the bias caused by the imbalanced data.
And then we focus on the question two. To assess and improve the classifier's performance, several key steps were taken. First, the data underwent pre-processing, where categorical variables such as gender, work type, residence type, and smoking status were transformed using one-hot encoding. Continuous variables like age, BMI, and glucose level were grouped into meaningful categories and encoded as well. Numerical features were standardized using standard scalar to ensure uniformity in score across features, which help improve the model performance. Addressing a class imbalance, synthetic minority oversampling technique was applied to generate a synthetic sample for the minority class, ensuring the model did not become biased toward the majority class. For modeling, LightGBM was selected due to its efficiency in handling large datasets, and a pipeline was created that combined SMOT and the LightGBM classifier. Hyperparameter tuning was performed using grid search CV, focusing on parameters like num level, leaves, learning rate, and N estimator, which directly affect the model ability to generalize and its learning rate. This was coupled with five-fold stratified cross-validation to ensure the model's robust by maintaining proportional representation of both classes in each fold. The model's performance was primarily evaluated using the F1 score, a metric that balances precision and recall, which is crucial given the imbalanced nature of the dataset. The best hyperparameter and the optimal cross-validation results were identified through the grid search. The classifier performance was feature validated by checking metrics such as accuracy, F1 score, and the confusion metrics on the training side. Finally, the model was used to make prediction on the test side, and the results were saved in the submission field. This step collectively aimed to optimize the classifier performance, handle class imbalance effectively, and ensure the model was well tuned for the best possible fit. Those are our projects, and thank you for listening and watching the video.